Many of you know I come from a bit of a life sciences background, so I ran into this idea called genetic algorithms, and I'd like to share what they're about with you. So let's dive right into it. What is a genetic algorithm? It sounds like a pretty complicated thing, but it's really not so bad, and hopefully by the end of this presentation I'll have demystified it for you guys a little bit, and maybe you'll even feel confident enough to try rolling your own. But the essence of it is that it's an optimization strategy that mimics natural selection. So basically our algorithms will be generating solutions to problems and kind of apply this principle of survival of the fittest to them. And so how do we make one? We need a few things first, namely a problem to solve. Depending on the kind of problem, we'll have to tailor our algorithm a little bit, but the overall steps are usually about the same. We're also going to need a fitness function. And what I mean by that is that we need a way to grade solutions, right? What makes a good solution? What makes a bad solution for our problem? And then finally, we need a way to represent these as DNA. This probably seems a bit vague to you guys, and it's probably unclear how this goes into code. So we're going to walk through an example. I think most of us have at least heard of the traveling salesperson problem. Essentially, the gist is given a set of cities, what is the shortest path that connects all of them, with the condition that your first city is also your last city, right? So it's a round trip. And I guess it's kind of appropriate that I'm doing this on our week 1 of Reacto and talking about algorithmic complexity. So you might imagine a naive solution to this would be to take all of our cities and actually generate every single possible permutation of routes between them. And that takes a really long time. It takes factorial time, which, as we know, with inputs even as small as 20 or 30 cities, begins to take an unmanageably long amount of time. So we're going to see if we could do a little bit better with our genetic algorithm. And so first, we're going to represent our routes as DNA with an ordered collection of cities. In my implementation, I ended up using an array. And basically the 0 index is the first city, the 1 index is the second city, and so on and so forth. And then also, again, pretty straightforward what our fitness function is, right? The shorter the path, the better. Basically, you would just go through a route, city to city, sum up all the distances, and then kind of rank them. So let's go a bit more into detail. Step 1 for our algorithm, we'll have to generate a seed population, kind of like a generation 0. And so say here we have cities 1 through 5, and we want to find the shortest route between them. Here I've just kind of randomly shuffled the cities 3 times, totally random, and then placed them in our starter generation. Then I'm going to rank the fitness of each of these routes. And so again, the shorter the distance, the higher the fitness. And then after that, we're going to randomly select 2 of these routes. I say randomly, and there's definitely an element of randomness to it, but usually the selection algorithm actually is biased towards the fitter ones. So the fitter you are, the higher chance you have of actually getting picked. And then, so this algorithm is modeled after biology, and so once